Hi guys, in the last video, we were able to introduce Karnaugh Maps, talk about their structure, their purpose, and look at a handful of examples to see how they really help us save time for Boolean algebra questions when really we can use a simple, visual, intuitive way. What we're going to be doing in this video is expanding on what we established in the last video so that we can see the important concepts like the bit flipping, the adjacency, and get better at solving more problems. There are going to be more problem solving videos, but what we're going to be tackling in this one are going to be majorly two variable Karnaugh maps. So let's get down to business. We have the two variable Karnaugh map, A, B, and output X. Zeros, not A, not B. So you can get the habit of writing not A, not B, not A, B, A, not B, A, B. Okay, so you can get the habit of doing this to make sure that you map things to your Karnaugh map properly. So let's get down to the crux of the matter. I have a line for B, draw our Karnaugh for X, and give ourselves a nice diagonal. So let's say we've got A on this side and B over here. So this is our Karnaugh map. Okay, a K map for the solution. So as usual, 0 to 1, 0 to 1. Not A, not B, and B. I do find out that labeling my maps this way, with all these extra terminologies makes my solution finding much faster. So not A, not B is straight up 0. Not A and B, so that 0 and 1 gives me 1. A and not B, so that's 1 and 0 gives me 1. And AB with output X gives me 1. Which is pretty cool. So we can easily see that we have 3. Yeah, out of the 4 possible states of this algebraic system, we have 3 where the output X is asserted, where we have a high on X. Okay, and since it's 3 is not a not a result of raising 2 to an exponent, to an integer exponent. So when you usually have 1, 2, 4, 8, etc., 3 is not part of that. So you do know I'm going to have more than one prime implicant group. Okay, and we can see that we can easily do that. This is going to be our first one, since it forms a nice rectangle. Okay, and this is our second group of implicants. We can see that here. So remember, the goal is to find expressions for each of these groups. So let's start with this one. Okay, so we see that this first cuts across both A and not A, so we know it doesn't depend on A, and it's only asserted in B, so we can call this entirely B, which is pretty cool. Same logic applies here. Cuts across both B and not B. So if something happens both while I'm doing something and both while I'm not doing something, then whatever it is I'm doing has no effect on whatever is going on. If it rains while I'm wearing my shoes and while I don't wear my shoes, then whether or not there are shoes on my feet have no effect on whether it rains today. Hope that analogy sort of makes sense. So then we can focus purely on A and see that this group is asserted only when A is high. So since we're dealing with the sum of products, we can now write our output X. So X is equal to A or B, which is, to those familiar with binary logic, is the same as the OR gate. And then you can now actually see it. That when you have either A or B or both of them asserted, you're going to have a high, but you're going to be low when neither of them are on. So that's the logic with binary. So let's get down to round 2. This time our output is on Z. So we draw the Karnaugh map as we would do usually. Okay, 1, 0, 1, 2. Both still have A and B. 0, 1, 0, 1. So this is not B. This would be B. Not A, and this is going to be A. Okay, so mapping from our truth table, because this is our Karnaugh map. Okay, it helps to label it. So this is your Karnaugh map, and this is your truth table. Okay, so not A not B is 1. That's high. Not A and B is 0. So where is that? A and not B is 1. A and B is 1. So this kind of looks like a flip of what we just encountered. So we can see first group of first prime implicant, second prime implicant. So you should begin to be able to get the hang of this by now, especially now that we're dealing with only two variables. You understand? So you can easily raise off your prime implicants. Okay, so starting with this, we know that this is entirely on A, so we're going to call this A. And then we know that this second group is entirely defined on not B, so we can call it not B. So then we can now say very easily and confidently that the simplest form of expressing this truth table is A or not B, which is simple enough to understand. The last thing we're going to tackle today is a peculiar two variable Karnaugh map. So from the get-go, you can identify that everything is asserted. All our outputs are high. So what does that really mean for us trying to make a Karnaugh expression for this? So we're going to have to draw the Karnaugh map to understand what's really going on. Okay, you should really be getting the hang of this by now. Okay, A, B, 0, 1, not B, B, 0, 1, not A, and A, 1, 1, high, high. So what do we really do? We call our definition of a group of a prime implicant. Okay, so we first of all need a rectangular or square region with, we're going to allow only, the only number of highs we're going to be allowed to be permitted are going to be 1, because it can be singular, 2, 4, 8, etc. So when usually in this situation, you could do this and this, and you would definitely still get a correct answer. Experience will show you that since these guys form a perfect 2 by 2 square, a perfect 2 by 2 square, and that gives us four perfect variables in a nice singular one-shot motion, we can make this grouping our entire prime implicant. So the entire of this truth table, the entire of this Karnaugh map is situated in one prime implicant. So what does that tell us? This prime implicant cuts across both B and not B, as you can tell, and both A and not A. However, it is true for all cases. So instead of saying A or B, or A and B, or whatever complex, I don't know, Boolean algebraic thing we can come up with, we would simply say that y is equal to 1. Because that is what it is. Irrespective of the combination of inputs, we have a high output y. So we can confidently make the claim that y is equal to 1, which is a case you may see in some examinations, but it's perfectly fine. It's definitely allowable. So in the next video, we'll try to solve more problems and get ourselves more familiar with 3 variable, 4 variable Karnaugh map expressions. So see you there.